Hi guys. So today I would like to start by going over one, two, three, four, five, six, about 7 questions from the exam that more than half of the students got incorrect. So I'm going to go over those questions. I will show you how to solve them. And then for the rest of the class, we will start chapter 16. So regarding the exam, um, only 8% of the students got A, and 23% of the students got B, 20% of the students got C, 10% got D, and 39% of the students got F. So I thought the exam was pretty easy, but I guess it wasn't. So if there's any feedback regarding the exam that you want to provide to me, I would love to take those feedback. So feel free to send email to me. Those of you guys got lower grades, I think I will have to curve this exam, but I'm currently not sure how much I should curve. Okay, so I will decide that by tomorrow, and I will make an announcement in the announcement section about regarding how much I'm going to curve the exam grade. And for those of you guys struggled for exam one, I highly recommend you guys scheduling an office hour with me and talk to me about the first exam material. Visit the SI sessions, visit SI office hour. Okay, again, schedule a separate office hour with me. I would love to help you with the exam one material. If you are falling back from exam one material, um, this is a good time for you to catch up and make sure you have a clear understanding of the first exam material, because chapter 14 and chapter 14 and chapter 15 contents are going to be included in the final exam. Final exam is comprehensive. Okay, so that's that. And yeah, I'm going to start by going over some of the exam questions that a lot of you guys struggled. Okay, so the first question was, oh, and then another thing is I'm going to create a survey on Web Campus today. It is not graded. It's just a survey. I want to hear your feedback regarding the study guide, whether it was helpful or not. Okay, so if it's helpful, then I'm going to make it again for next exam. But if it's not particularly helpful, then I'm just going to focus on making the charts that you have to memorize. Okay, so please participate those surveys, so I know what to prepare for next exam. Making the study guide took a long time for me, so if it wasn't that particularly helpful, I don't want to waste too much time on it. I can just focus on making the charts that contains list of things to memorize. Okay. So the first question that more than half of you guys got incorrect was this rate law question. Okay. The data was given, okay, and the question was asking you to find the rate law. This is a very similar exercise from the sample exercise 14.6 that we did in the class, and you guys solved similar problems for the homework as well. Okay, but I'm just going to go over it with you guys one more time. So looking at experiment 1 and 2, you can tell that while concentration A was held constant, when you increase the concentration of B, the rate stayed the same. This tells us that experiment 1 and 2 tells us that this reaction is independent of B's concentration. Even if you double the concentration of B, the rate didn't change. Okay, this means that the reaction is zero order in concentration B. Okay, so from experiment 1 and 2, we immediately know that the rate is dependent on concentration of reactant A only. Okay, let's take a look at experiment 2 and 3. These two experiments show how order of rate law with respect to concentration of A. Rate, so I'm examining here between 2 and 3. Okay, rate 3, the ratio of rate 3 over rate 2 equals rate constant K, concentration A from experiment 3 divided by rate constant, concentration of A in experiment 2. We know that the rate constant is same throughout the experiment, so these two cancels out. Okay, if we plug in the numbers that's provided, rate 3 is 10.17 divided by rate 2 is 1.13. Concentration of A in experiment 3 was 1.35. Concentration of A in experiment 2 was 0.451. Okay, this, if you do the math, put these values in the calculator, you have 9 equals to 3 to the power of m. If you solve for m, you get 2. What does this 2 tell you? This tells us that since the rate increases by a factor of 9 when concentration of A is tripled, the rate law is second order in A. I'm going to write that down. Since rate increased by factor of concentration A is tripled. Okay, when you tripled concentration of A, this increased by a factor of 9. The rate law is second order in A. Okay, so the rate is going to be rate constant times concentration A to the power of 2. Okay.
Professor?
Yeah.
Sorry. I'm just a little confused on how you figured out that the concentration of B was zero order.
Concentration of B was 0 to O. So if you look here, focus on these focus on this part. Focus on this part. Okay? When the A concentration is held constant in experiment 1 and 2. When you increase concentration of B, did the rate change or not? Yes or no?
No.
No. That means that tells us that concentration of B does not affect the rate.
Okay, I see it
Yeah?
now.
Okay.
Yeah.
So here. So this reaction tells us that the reaction is independent of B's concentration. We can
Okay.
say that, yeah, the reaction is zero order in B. So the B does not participate in the overall rate equation. Okay?
Okay, thank you.
Uh-huh. All right. Moving on to second question that more than half of the class got wrong is okay. It was this question. The equation was given, and the question asked us to determine the molecularity and the rate law. Okay, so molecularity is a number of molecule present in an elementary step. This is a single elementary step. Molecularity is number of molecule present in an elementary step. Okay, so you have 1 and 2 molecules present in the elementary step, so the molecularity is going to be 2. The rate law is going to be concentration of reactants multiplied together. That's it. Okay. Third question that a lot of you guys got incorrect was oh no. Where two different elementary reactions were given. Actually, they're not elementary reactions. They're two separate reactions. Okay. So the equilibrium constant of Kc for reaction 1 was given. It's labeled as K. And then they wanted us to find the equilibrium constant for reaction 2. I'm going to write experiment 1, experiment 2. Okay. What can you tell from the relationships between these two? The experiment 2 is basically a reverse reaction of experiment 1. Okay, or equation. Reaction 1, reaction 2. Okay, basically reaction 2 is a reverse reaction of reaction 1. Not only that, the reaction 2 is reaction 1 multiplied by 2. Okay, so you have two things. Reaction 2 is reverse of reaction 1. So then, according to the, if you look at the study guide, we have formulas for these cases. Okay, so if you have a reverse reaction, then the equilibrium constant is going to be equilibrium constant for reverse reaction is the reciprocal of the forward reaction, equilibrium constant of the forward reaction. Okay, so the K2 equilibrium constant for the reaction 2 is going to be 1 over K. Reaction 2, not only it's reverse of reaction 1, it is multiplied by 2. And if it's multiplied by 2, you need to raise the original equilibrium constant to that power. Because it is multiplied by 2, the K2 is now going to be equilibrium constant of the original reaction raised to the second power. So then the new equilibrium constant for this reaction is 1 over K squared. Okay. Moving on to next question. Very similar type of question as the previous one. So the Kc value of this reaction was given. 5.4 times 10 to the power of 13. Okay, and then the question was asking for Kc value for this reaction. Okay, again, this second reaction is basically reverse reaction of the first reaction. Okay, so the Kc of reverse reaction is reciprocal of the forward reaction. So the Kc2 is going to be 1 over 5.4 times 10 to the 13. So it's, you just have to plug it into the calculator, do the math, but I was so surprised that more than half of you guys got this question incorrect. It's this value, but for scientific notation, you're not allowed to have a number below 10. So if you rearrange this, or 1.9 times 10 to the negative 14. This number is higher than 1, lower than 10, so appropriate as a scientific notation.
Professor,
Yeah.
how can we check and see what questions we got wrong?
Oh, you can't. I don't show the exam to the students.
Okay,
Yeah.
thanks.
Mm-hmm. If you want to see your exam, you can schedule an office hour with me. But other than that, I don't release the exam to the students. Four, 5. Okay, moving on to next question. All right, Le Chatelier's principle. About 60% of students got this question incorrect. The question I was asking, when you remove a component, from equilibrium mixture, where does reaction shift? Let's say you're performing a reaction A plus B generating C. This reaction is at equilibrium. If you remove a component from equilibrium reaction, let's say you remove C, then the reaction will shift to the direction producing more of the removed component, right? So if C is removed, it's going to shift to a direction so that the reaction can produce more C. Let's say if you removed B, then the reaction is going to shift towards direction to produce more B. Okay, so the answer is when you remove a component from equilibrium mixture, what's going to happen is then the reaction is going to shift to direction of producing removed component. Okay, and same thing for the opposite situation. When you add a component to the equilibrium mixture, the equilibrium system does not want that added component. So it's the direction of the reaction is going to shift to a direction where it can use up the added component. Okay. All right, last question. Question 8. Give me 1 second, please. I'm looking for the question. Okay. The following reaction is second order in A and the rate constant. So given this equation, the reaction is second order in A. Okay, and then it says the rate. Then from this statement, we automatically know that the rate is rate constant K times concentration of A to the power of 2, because it's second order in concentration of A. And then the question also provided the K equal rate constant value to be 0.025 inverse mole inverse second. Okay, and then it was given concentration of A at time of 33 seconds to be 0.65 mole. T is 33 seconds. Okay, and the question wants you to find initial concentration. Okay, because this is a second order reaction, we need to bring the second order reaction equation, which is 1 over KT. Okay, so as you can see here, we have concentration, later concentration, we have constant, we have time, we have all the information we need. We just have to solve for the initial concentration. Okay, so let's plug in all the numbers that we already know. Later concentration is 0.65 mole minus equilibrium, the rate constant is 0.025. Every 3 seconds. If you do this portion of the math, you get 0.825 inverse mole. Second cancels. And then if you do this math, you have 1.538 inverse mole minus 0.825 inverse mole, that is 0.713 inverse mole. Okay, so then we have 1 over initial concentration of A equals to 0.713 inverse mole. Initial concentration of A is going to be 1 divided by 0.713 inverse mole, that is 1.40 mole. Okay, so if you memorize this equation, this question would have been very, very easy. One last question that I want to go over is this is question 9. Wait, is it 9? 5, 6, 7. Okay. With this equation, the question was asking what can increase the rate of reaction. The given information that the rate is rate constant to the second order of A. So this tells us that the rate is 0 order in B. The rate is independent of concentration of B. Independent of B. The choice was the question was asking what would not affect the rate. Okay, what would not affect the rate? So because the rate is dependent on A, if you increase the concentration of A, this would increase the rate. If you increase the temperature, it will also increase the rate. Adding catalyst lowers the activation energy, it will increase the rate. The only factor that will not affect the reaction rate is concentration of B, because the rate is 0 order in B. The rate is independent of concentration of B. Okay. So those are the exam questions that I wanted to go over. These are the questions that more than half of the class got incorrect. If you want to go over other questions in the exam, you can feel free to schedule an office hour with me. I would love to go over the details with you guys. Okay, so that's that for the exam. Again, I will put an announcement regarding the how much exam grade I'm going to curve. I will make the decision by tomorrow, and then I will post in the announcement section by tomorrow. All right, so let us start chapter 16. Okay, let me know if you guys, if your screen is frozen, okay? Because mine froze for a little while. All right, for chapter 16, we will be learning about acid-base equilibria, okay? Acid and bases are among the most important substances in chemistry, and in this chapter, we will thoroughly study number one, how acids and bases are identified and characterized. Number two, we're going to study how we measure the acidity of the compound. And number three, we're going to learn how the chemical reactions of acids and bases depend on their concentrations. Okay. So there are two different types of definitions of acid and base. So the earlier definition was developed by Arrhenius. He came up with definition of acid and base first, and he stated that an acid is a substance that increases the concentration of hydrogen ions when dissolved in water. Okay. A base is a substance that increases the concentration of hydroxide ions when dissolved in water. This is hydrogen ions. This is hydroxide ions. Okay. For example, if you dissolve hydrochloric acid in water, you will get hydrochloric acid will dissociate and produces hydrogen ion and chloride ion. Because hydrogen increased the concentration of hydrogen ion when dissolved in water, hydrochloric acid is considered Arrhenius acid. So that's the definition of Arrhenius acid, or now base. However, the Arrhenius concept of acid and base is rather limited because it's restricted to aqueous solution which involves water. Okay, so the later Danish chemist Bronsted and English chemist Lowry, they both came up with new definition of acid and base. So according to this Bronsted and Lowry, the definition of acid base involved transfer of proton is same as hydrogen ion. Okay, so according to Bronsted and Lowry, the definition of acid base involves transfer of proton ions or hydrogen ions or proton. Okay, so from now on, if it's hydrogen ion, I'm just going to say proton. Okay, according to them, any substance that donates the proton is considered acid. Any substance that receives proton is considered base. Okay. So according to Arrhenius, he expressed hydrochloric acid and water equation as this. But in reality, this hydrogen ion that has formed, it doesn't stay alone for too long. The hydrogen, what's going to happen to the hydrogen is the hydrogen ion is going to immediately interact with other water molecules in the system, and it's going to form the hydronium ion. Okay, you see how this proton quickly reacts with other water in the system, and this is hydronium H3O plus. It's going to generate the hydronium ion. Not only that, the hydronium ion that has been formed will interact with other molecules. See, hydronium ion interact with other molecules to generate further ions such as H5O2 plus, H9O4 plus. So therefore, when acid is in aqueous solution, water, chemists use notation hydrogen ion and hydronium ion interchangeably. Okay, it is uncommon for hydrogen ion or proton to stay by itself as Arrhenius depicted. Okay.
Sorry, so these two mean the same thing, right?
What two things?
The H plus and the H3O plus.
So they are obviously technically different things, but what I'm saying is the chemists use these notations hydrogen ion and hydronium ion interchangeably. Does that make sense? They are technically two different molecules, two different types of substances. But because hydrogen ion never stays alone, it will when it's in water, it will immediately interact with other molecule and form this. So what I'm saying is that the chemists will use this term interchangeably. They are not same. Okay?
Yeah, it makes sense. Thank you.
So let's take a closer look at the Bronsted-Lowry definition of acid and base. According to the Bronsted and Lowry, acid is any substance that donates proton. Okay? Base is any substance that receives proton. Okay? In this example, hydrochloric acid is donating its proton to water. See, water now has proton donated by hydrochloric acid. Okay, so hydrochloric acid, which is donating its proton to water, is Bronsted-Lowry acid. Water which is accepting the proton, is a Bronsted-Lowry base. Okay, so Bronsted and Lowry acid base are all about proton transfer. Who donates proton and who receives proton. So I myself often like to think that the base is stealing proton from acid. Okay, I often like to think that the base is a bad guy, it's stealing the proton, and acid is a good guy, it's donating or willing to give up the proton. Okay. So from the previous slide, water molecule accepted the proton from hydrochloric acid, or water stole the proton from hydrochloric acid. So it was a Bronsted-Lowry base. However, water is a pretty interesting molecule because it can also act as an acid by donating its proton. Okay, so therefore we say water is amphiprotic because water is capable of acting as both acid and base. Act as acid. Acid and base. Amphiprotic. Okay, so if you look at the example over here, when ammonia is added to water, water donates its proton to ammonia, or ammonia is stealing proton from water, generating ammonium ion and hydroxide ion. Okay, so now because water is giving up its proton, water is a proton donor. In this case, water is considered Bronsted-Lowry acid. So far we've learned about two different definitions of acid and base. We've learned about Arrhenius' definition and Bronsted-Lowry definition of acid and base. We've also learned about the amphiprotic substance that can act as both acid and base, right? So now that we have all the basic definitions of acid and base covered, we will move on to the next concept, which is conjugate acid and conjugate bases. So, for example, consider this acid-base equilibrium reaction between nitrous acid, this is nitrous acid, and water, okay, forming nitrate ion and hydronium ion, okay. As you can see from the equation, in the 4 reaction, nitrous acid is donating, nitrous acid donates a proton to water, okay.
Dr. Lee,
Yeah.
I'm sorry. So then this is the third form of acids and bases?
No. This is like an extended concept.
Extended concept?
Yeah. So we've learned about basic concepts of acid and base. We're gonna learn about extension of acid and base. So it is acid and base.
Thank you.
Mm-hmm. So yeah, for the forward reaction, nitrous acid donates a proton to water. So when nitrous acid loses its proton, it becomes nitrite ion, okay? These two molecules, what can you tell from these two molecules?
The charge also changed?
These two molecules differ by presence or absence of a proton, correct? These are called conjugate acid-base pair. We say nitrate ion is a conjugate base of nitrous acid. We say nitrite ion is conjugate base of nitrous acid. So conjugate base of this acid is going to be nitrite ion. Conjugate acid base pair differ by presence or absence of a proton. Okay? Differ by proton. So these two are the conjugate acid base pair. So also in the 4 reaction, let's take a look at water. Is water receiving proton or donating proton? Water is receiving proton from nitrous acid, or water is now stealing proton from the nitrous acid. Okay, so when water accepts a proton, it becomes hydronium ion. Water and hydronium ion are also conjugate acid base pair. The only difference between water and hydronium ion is having a proton and not having a proton. Having an extra proton, not having an extra proton. Presence or absence of proton. So we say hydronium ion is a conjugate acid of water. Okay, so always acid will be the one that has extra proton. Okay, it needs to have extra proton so that it can lose, right? So between these two, which one has more proton? Hydronium ion has more proton. So this is an acid. Okay, this is a conjugate acid of this base. Between nitrous acid, nitrite ion, which one has more proton? Nitrous acid has more proton, okay? So nitrous acid has one more available proton to donate or lose or give up. So this is an acid, okay? So if you're unsure which one is a base or which one is acid, you need to consider the number of proton they have it in the conjugated acid-base pair. All right, let's try a sample exercise about conjugated acid and bases. So for A, we need to find conjugate base of following acids, okay? In order to find conjugate base, we simply have to remove a proton from these acids. To find conjugate base, we need to remove a proton from these acids. Okay, so conjugate base of the perchloric acid, it's going to be, if you remove one proton, it's going to be perchlorate ion. Okay, conjugate base of the hydrosulfuric acid, if you remove one hydrogen, you have hydrosulfide ion. Conjugate base of phosphonium is, if you remove one proton from here, we have pH 3, which is phosphine, bicarbonate. Conjugate base of bicarbonate, if you remove one hydrogen, it's going to be carbonate ion. Okay, so in order to find the conjugate base, simply remove a proton. Question B, you need to find conjugate acid. Okay, so in order to find conjugate acid of the following bases, you simply have to add a proton to these bases. To find conjugate acid, we need to add a proton to these bases. Okay, so the first base we have is the cyanide ion. Conjugate acid of the cyanide ion, if you add a proton, it's going to be HCN, which is hydrocyanic acid. For sulfate ion, conjugate acid of sulfate ion, if you add a proton to this, you have hydrogen sulfate ion. Conjugate acid of water, very easy, we've done this many times. Hydronium ion. Conjugate acid of bicarbonate. You add a proton to here, you have carbonic acid. Okay. So, what can you notice? Bicarbonate. Notice that hydrogen carbonate ion is amphiprotic. It can act as either acid or base. Okay, so in this case, it's acting as an acid, losing proton, generate conjugate base. In this case,
Professor?
yeah.
So with the first example with the conjugate base, shouldn't the charge after, shouldn't that be -2
Which one?
or no? So for the HCO3, when you
Oh,
remove
so
a
in order,
proton,
yeah, in order to completely balance, you need to have 2 hydrogens. But then you only have 1 hydrogen, so it still has charge of -1.
oh, okay.
Yeah.
Thank you.
Oh, are you talking about here?
Yes.
Yeah, my mistake.
Okay, thank you.
So yeah, thanks for correcting me that. So the what is it? Bicarbonate, hydrogen carbonate ion is amphiprotic. It can act as an acid. In this case, it's losing its proton, and or it can accept, or it can steal the proton from something else and generate the acid. Okay, so it can act as a acid or base. So let's try another sample exercise about conjugate acid-base pairs. In this exercise, you have to write an equation where hydrogen sulfide ion act as acid in water and also act as a base in water. Okay, it is amphiprotic. Question A, we're going to write a chemical equation where hydrogen sulfide act as an acid. Okay, act as an acid. So because it's acting as an acid, it should donate a proton, or it will give up the proton, and after losing its proton, on the product side it should have conjugate base of the hydrogen sulfide, which is a, if it gives up the proton, you're going to have sulfite ion. Now water is receiving the proton, so you have hydronium ion. Question B, it says hydrogen sulfide is acting as a base. Okay, in that case, because it's acting as a base, it should receive a proton from water, or it will steal the proton from water. After gaining the proton, the product side should have conjugate acid. It should have conjugate acid of hydrogen sulfide, which is sulfurous acid. After adding 1 more hydrogen, and then because now water is donating its proton, it lost its proton, so you have the hydroxide ion. All right, so it says the question asking us to identify the conjugate acid-base pairs. Okay, so the conjugate acid-base pair for question A is going to be hydrogen sulfide is an acid, and the sulfite is going to be conjugate base. Okay. Water is acting as a base, and therefore hydronium ion is going to be conjugate acid. Okay. For equation B, the hydrogen sulfide is acting as a base, so it is a base. The form that has extra hydrogen is going to be conjugate acid. Water is donating its proton, so it's acid, and the form water, the form that water, after losing its proton, is going to be hydroxide ion, is conjugate base of this acid. Okay? Let me know if I'm going too fast. Okay. I forgot to add this diagram on this slide. But okay, moving on to next concept. So how do you know when will a molecule donate the proton or accept the proton? Or how do you know when will a molecule act as an acid or a base? So the relative strength of acid and bases determine whether a molecule will donate or accept the proton. Okay. So some acids are going to be better proton donors than the others, and some bases are better proton acceptors than the others. If we arrange acids in the order of ability to donate a proton, we have a chart look like this. Okay. This is the acid strength increasing. The stronger acid would readily donate the proton, or it will love to give up the proton. Conjugate base of these strong acid is a weaker base, which means they less readily accept the proton. Okay, so strong acids will have its conjugate base as a weak base. Okay, so here it says acid above the line with water as a base. Acid above the line, water as a base here. These acids, okay, acids above the line with water as a base are strong acids, and because their conjugate base are weaker base, what happens is that when you dissolve strong acid into water, such as, let's say you dissolve hydrochloric water, what's going to happen is hydrochloric acid would completely donate its proton to water, and the chlorine, because it is a weak base, essentially will have no tendency to accept a proton. Okay, so I'm going to summarize what I just said. Strong acid has weak conjugate base. Okay, so let's say, for example, you have hydrochloric acid dissolved in water. If you have proton in hydrochloric acid dissolved in water, this conjugate base of hydrochloric acid is a very, very weak base. Okay, so it has no tendency to accept the proton and go back to proceed the reverse reaction. Okay, the conjugate base of the strong acids have negligible or extremely low basicity. It has extremely low tendency to receive a proton. It is very rare that these bases receive a proton. Okay, so this is a sentence that you need to keep in mind. Strong acid will have weak conjugate base. So what about the strong base? Strong base would readily, these strong base, they would readily accept the proton, or it will love to receive the proton. The conjugate acid of the strong base is going to be weaker acid, which means these acids less readily donate proton. Okay, so bases, here it says bases above the line with water as an acid. So the bases above the line, water as an acid, they're talking about these bases are strong bases, and because their conjugate acid is such a weak acid, they don't really act as an acid in water. Okay? Strong base has weak conjugate acid. Okay? So this means that conjugate acid of strong bases have negligible or extremely low acidity, and they have no tendency to donate a proton. It is very rare that these acids donate a proton. Okay, so this is a takeaway. Strong base has weak conjugate acid. These conjugate acids, they have extremely low acidity. They have almost no tendency to donate a proton. Okay. So any substance between the lines with water here are weak acid and weak bases. Okay, these are weak acid, weak bases. Okay, weak acids have conjugate bases that are weak bases, vice versa. So if you put these acids in water, the conjugate bases have slight ability to receive and accept protons. Okay, so 3 things to remember from past 2 slides. Number 1, strong acids have conjugate bases with extremely weak basicity. Strong acid has conjugate base with extremely low basicity. Number 2, weak acid will have conjugate base with weak basicity. Extremely weak acids. So the one with the negligible acidity, extremely weak acids will have conjugate base with strong basicity. Okay, so these are the 3 things to take away from past 2 slides. Okay. So when we don't know whether an
Professor,
acid, yeah.
sorry, could you go back? I just need to finish
Oh,
writing
sure,
something
sorry.
there. Thank you.
Let me know when you're done.
I'm done. Thank you.
Okay, so why is this important? Why is this relative strengths of acid and bases important? It's important because when we don't know whether an acid-base reaction would lie to the left or right, we can compare the acid and base strength. Okay, The proton transfer reaction in acid-bases reactions are governed by how strongly bases attract protons. How strongly bases attract protons, or how strongly bases steal the protons. Okay, so how strongly bases attract protons is very, very important. Let's take a look at the first reaction. On the reactant side, water is a base. Water is a base, okay, because it's receiving proton. On the product side, chlorine is a conjugate base of hydrochloric acid. Okay, if we compare the basicity of two bases, compare basicity to bases. Let's compare the basicity of these two bases, water and chloride. Water is here, chloride is here. Which one is a stronger base? According to this chart, water is a stronger base than chlorine. Water is a stronger base. Therefore, the reaction is comfortable transferring proton from hydrochloric acid to water. Because chloride is such a weak base, this ion would never attract any proton. So the reverse reaction would never occur. Why? Because chloride is such a weak base. It has zero or very, very, very low tendency to steal proton. Okay? That's why, therefore, for this reaction, the reaction lies completely to the right, product side. Therefore, we use one arrow. Okay, so the relative strength of base is very important in determining whether the reaction is going to lie to the right or left, or it's going to be both directions. Okay,
So,
let's look at the
sorry,
yeah.
Professor. So just an example. So if water were weak, like a weak base, would the direction of the equation be towards the left?
Of course.
Okay.
Yeah.
Thank you.
Mm-hmm. So if think of it this way, find the weak base from the reaction. Okay, if there's any side of the reaction that contains weak base, the weak base has no capacity to steal the proton, so this reaction would rarely occur. Does that make sense? Okay, all right, so let's take a look at the second reaction. On the reactant side, water is a base and conjugate base of acetic acid is going to be acetate. This is a conjugate base. Again, compare the basicity of two bases. Let's compare the basicity of these two bases, water and acetate. Let's go back to the chart. So water is right here and acetate is right here. Which one is a stronger base? Acetate is stronger base, okay? Therefore, what does this tell us? Therefore, it will be very likely that acetate would steal the proton from hydronium ion. It is very likely that acetate would receive proton from hydronium ion, okay? And the reverse reaction would occur. So the reverse reaction is favored more than the forward reaction. So the equilibrium actually lies to the left. However, we use both arrow because the basicity of two acids don't differ much. The reaction favors the left side, but the forward reaction is still occurring, so we still keep the two arrows. However, the K value, the equilibrium, favors the left side. Okay, so this is an example where equilibrium favors the right side, favors the product. Sorry, favors the reactant side. This is an example where the equilibrium lies to the right, where equilibrium favors the product. Let's try a sample exercise to get a better idea, right? Let me read the question. For the following proton transfer reaction, use figure, this is a figure, to predict whether the equilibrium lies to the left or lies to the right, okay? So for this question, we need to determine whether the forward reaction is favored or reverse reaction is favored. Again, the very first approach should be identifying basis. Identify basis, okay? And then compare the basicity. Okay, so on the reactant side, carbonate ion is a base because it is a receiving proton or it is stealing proton. On the product side, sulfate ion is a conjugate base of the hydrogen sulfate ion. So let's compare the basicity of these two bases. Carbonate is right here, and sulfate is right here. So which one is a stronger base? If we compare the basicity according to this chart, carbonate is a stronger base. That means it is more likely that carbonate to steal proton from hydrogen sulfate ion than bicarbonate to steal the proton from sulfate ion. Okay. It is more likely for carbonate to receive proton from hydrogen sulfate. Okay, so that therefore the forward reaction occurs more readily. So then where does the equilibrium lies? Equilibrium lies to the right, favoring products. Okay. Kc is larger than 1. Okay. So in a simpler explanation, because this is such a weak base, it almost does nothing. Okay, it has very, very low capacity to steal the proton and make the reaction go left side. Okay, because this is such a weak base, this reaction would rarely occur. Okay, so therefore the reaction, the majority of the reaction is going to occur to the right. Okay, this direction. All right. Oh, I went over time. So that's the end for today's lecture. If you have any questions about the exam, please email. I will create a survey about the exam study guide today. Please participate the survey. And yeah, I can't stay for another 5 to 10 minutes today. I'm going to end the meeting. So if you have any further questions, please email me. And if you want to provide any feedback for the exam, I would love to hear the feedbacks about the exam through email. So let me know. And yeah, I'll see you guys next Tuesday. Bye, guys.